Hey there, welcome back to the channel. My name is Chris, and today we're going to continue the series of talking about how we can replace an automotive relay with a MOSFET. First, let's just do a real quick review of what we did last time. What we did is we created a high side switch using this P-channel MOSFET switched by an N channel. And let's just cover this real quick so that we understand how this works. What we're doing is we're switching the high side to give our load. So we're providing 12 volts to our load, and then the load is grounded. Load might be a lamp, might be a fan, something like that, right? Something that takes more power than we want to drive from something like a microcontroller. So P channels and N channels work differently. A P channel, when the gate is high, this is open. So it's an open circuit while this is on. So effectively, this being on makes this off, whereas an N channel works opposite. When this is on, and when this is off. So what we're doing is we're switching the gate inverse of what we want. So let's just logically look at how this works. When this is off, we have this pull-up provides 12 volts here. So when this is off, we have 12 volts, and this is therefore energized, so this is an open circuit, and then this would be off. If we close this, basically connect this to ground, and you can do that just with a switch. Connect this direct to ground, and it would turn this on. That's a real easy way to do all of this. There are a lot of problems with doing that. It's slow to switch, it's very inefficient, and you could have some problems causing burnout. But what we've done is, since we want to switch from something like 3.3 volts or 5 volts, we added this in here. So basically, this is acting like a switch to ground activated by this. And when I build it, it looks like this on a breadboard. This is just the physical version of what we just saw in the schematic. So we've got our MOSFET here. This is the P channel. This is an N channel MOSFET, low current, with those resistors. Now, this is not an ideal thing to be using in an automotive situation for a variety of reasons. One is, so this is our source voltage here. So this would be basically what's coming out of the alternator. If we get a spike on this, what can happen is it will actually blow through from here to the gate, and then all of a sudden you've got this voltage coming through over to this. That is, generally speaking, not an ideal situation. Not only does it ruin this MOSFET, but you can end up getting voltage that feeds back, and especially if it cascades, it can come all the way back to your microcontroller. Another problem that you might have is if we hook an inductive load up, so our output, it's kind of hidden under here, that red wire, but that is our source that's going out to our load. If you're running something that's inductive, a fan or something, you can actually end up getting power that comes back on through here when it switches on or off. And so you get reverse voltage in this that can also cause a problem. So you'd want to protect against that. There are some other protections that you can do over here on this driver or this switching MOSFET. And so what we can do is we can actually replace this with something that is more robust, that is designed to actually drive one of these. It's called, not surprisingly, a driver. So what we're going to do today is we're going to replace this with a driver and add some protection over here to make this a more robust circuit. Then what I'm going to do is show how to drive the resulting circuit from either a physical switch, so you could just put a switch on your dashboard and drive this, or you can drive it with a microcontroller. Let's go draw out what that improved circuit looks like. For this circuit, we're going to use this same P-channel MOSFET. This is an IRF 9540. This is going to connect to our load. This is going to connect to our system voltage. We'll just call it 12 volt, though we know it runs probably about 14.5. Now we're going to, again, we're going to have a gate resistor here. and put that at about 100 ohms. I did see in some of the previous videos people saying, well, there shouldn't be any current here. In steady state, there is no current. But when you turn this on and off, current has to flow in or out because this is basically a capacitor. So you need something to decrease or at least limit that flow of current going in and out, especially because these are really fast. The faster you drive this, the more current has to go through this. And in my case, I want to drive a PWM, so we want to switch this fast. Now, here on the input, instead of what we had before, we are going to use a chip that is called a driver. And this one has, 8 pins, but really, I think 4 of them are connected to each other. So you've got 2 grounds, 2 outputs, and 2 powers. So it's really not a lot of connections. This is a TC4420. And basically, these drivers have an out and an in. It's also powered. So we're going to power it from the same system voltage, and it needs a ground. And then it has an input. Now, the simplistic way to do this, if we just wanted to drive this with a switch, like inside the vehicle, what we can do is we can take this and put a pull-up resistor here, put a 10K in, and then we could connect this through our switch to ground. And that's all we need. This will provide everything that we need in order to turn this on and off. But again, we know that we've got some problems that we just discussed where we need to add some protection. One of the first things is if we get a voltage spike that comes through our line here, to protect this, we can attach a Zener diode, and we'll put in, say, an 18-volt Zener. So what happens here is if we get too much voltage, instead of it basically coming through and blowing through this spot between the source and the gate, it will equalize between the two and not cause there to be a huge difference between the two when it's above 18 volts in order to protect it from blowing through there. And again, we had said that if we have an inductive load, we want to put something in here. So we can put in a diode. And this was the same 12 volt to here. And for this, we would use something like an RL207 diode. Note that over here, if there's a spike, I don't have any protection, so a TVS somewhere over here would probably not be a bad idea. Also, highly advised to put a fuse in, like right there, off of your 12 volt. So that if you have super high current, something goes to ground here, it doesn't just cook everything. So let's go take a look at how this works physically before we even hook up a microcontroller. We'll hook one up over here, but first let's drive this with just a switch to show how that all works. And I was not paying attention. We also do have to have in here our pull-up on this one as well. So that's a 10K pull-up. That is so that if this is not asserted to any state, this is high, which makes this open. If you watched the previous videos, this setup should be fairly familiar. We've got our circuit here. I'm just driving this PC fan, so this is a 12 volt fan, and I've got 12 volts coming in here. Now, here again is that MOSFET. This is our driver. Here is our flyback diode. This is the Zener diode. This is the gate resistor. This is the pull-up for the gate here on the MOSFET. And this is the pull-up for the input on the driver. Now I'm just going to take this simple switch, right? Just an on-off switch. We're going to hook it up. And I'm going to go to ground. And the reason I'm going to ground here is because in vehicles, typically that's how they work. Like an ECU or something, they don't provide power to a circuit. They provide a ground path for power. And so when something needs to turn on, you just drive it to ground, and it turns on. And then we open that up, and it shuts back off. So really what we have is a switch that you could have this, right inside the cabin or whatever, and it connects to chassis ground, and it turns on our load. So this is a high side MOSFET switch that has some protection for use in a vehicle. Now the nice thing here is this is really easy to adapt to take a microcontroller to drive it instead of just this switch. It also has some other advantages in that these are both very fast components, so I can switch on and off really quick, like, in the nanosecond range, which is very useful if I'm using a PWM to affect the voltage or the apparent voltage of the output. We'll talk about that in a future video when we're building a controller for a glow plug, but for now, let's go take a look at how we would drive this from a microcontroller. Driving this from a microcontroller, basically we don't want this switch anymore, but we want an input to our circuit from the output of a microcontroller. This is actually really, really easy. What we're going to do is we're going to use something called an optocoupler. We're going to have a resistor in here because this optocoupler is effectively inside an LED and then a phototransistor that it shines on to close it. So this will come in, and then we have this goes to ground. Remember, all we're doing before we just switch to ground, we're going to be doing the same thing. This switches to ground, and we provide power here. So if we provide power here, it turns on an LED inside of it, which connects these two together, which drives this to ground. The nice thing about an optocoupler is this physically separates all of this from all of this. So we've got our 5-volt side and then things that could be up around 12. So if something happens and somehow this voltage ends up feeding through some of these things, it will stop here. It will not transfer over into our 5-volt side. For this, I'm going to use a PC817. So let's wire this up and see how that works with a microcontroller driving it. This is that optocoupler. So our input comes through this 330 ohm resistor. Again, comes from our Arduino here through that 330 into the optocoupler and then also to ground. So we've got our LED here and then our photo transistors up on this side. So now if I power this, you can see it turns it on, and you can see it cycling on and off. It only comes on for a short period of time and then shuts back off because this thing coasts quite a bit. It's also worth noting that we do have a TVS diode and some other things over here that are helping to protect this circuitry up here from the 12-volt system. So when it's all combined, this is a pretty reliable automotive safe circuit, and then we can use this to drive some other things. So really the next thing we need to do is we're going to take all of these and put them onto an actual circuit board and solder it down so that we don't have these wonky breadboard connections, and we're going to drive a glow plug that definitely consumes way more current than this. This is probably about 150, 180 milliamps, whereas a glow plug is probably going to be pulling 10 to 15 amps. And that's all I got for you today. So again, relays, they're great. They do the job for a lot of things, but they are slow. They cannot switch quickly. If you need something that switches fast, a MOSFET is the way to go. You could also use a MOSFET for a lamp. You don't have to use a MOSFET, but you also don't have to use a relay. Like most things in electronics, you have options. Choose what works best for your application. Thanks for watching.